we are actually in this missing data handling, right? So in earlier classes we know that there are three ways to handle the missing data. Way number one is what will be deleting the entire value, entire row containing the NA value, or entire column containing the value. The one is what will be deleting the entire value, entire row containing the NA value, or entire column containing the NA value. So this is actually the computationally easy step. But what happens is if I do these steps repeatedly for my data set, then a fraction of data set will be removed by these missing data removal itself. So if I have a very large data set and the removal of these NA values will not affect my data sample size, then I can go with deletion. A computationally easy step is the deletion of these values. Second is the most effective step, but not an efficient step, that is model development for missing data. I can develop a model for those values which is actually missed by keeping those values as output values, and other values which to which I don't have any NA, I'll keep those as train and I'll develop a model. And I'll get an equation. Using that equation, I can find whether the new feature which is actually having NA values. But what is the drawback here? If I have more number of features, then I have to develop that much equations, meaning that I have to develop that many number of models, which is actually computationally complex. So this is actually a computationally expensive step, not suitable for real-time data analysis. So we go to the third one, which is actually leveraging the statistics, mean, median, and mode. So if I want to calculate NA, I want to fill my NA value, then what I do, I take the mean of the distribution and substitute the mean to all the NAs in that particular distribution. So what happens is all the distribution may have same values, all the NA values will be replaced by the same mean. Instead, I can also go for a conditional mean where a group of similar items can be taken and the mean of those items alone can be replaced for the NA value of the corresponding row. For example, if I have some age values, let us see here. See if I have the age value here. See, my age may have some NA values. And what I do, I go to the sex, I have male as well as female. So what I will do, I'll take only the male values in the distribution, take the mean of only the male and substitute it to the male NA values. Here and now I will not say that age is NA. Instead, I will categorize age into two. Age and the age values having NAs into two. That is male ages NA and female ages NA. So all the male NA ages will be replaced by the mean of all the male ages. Female age NAs will be replaced by all the female ages. So this is actually conditional mean, that is for finding for filling the NA values of one column, I am taking the results of another column. Say for example, if I want to fill the NA values of age, I take the gender also into consideration, right? Based on either male or female, I fill it. Right, so we did some analysis yesterday. So this is actually like the previous class. This is actually the common step used in any text data analysis, where we took the data, we just viewed the first head, but this head shows that only cabin is having NA values, but some other values may also have NA, but not in the first 5 rows. So do we have to check that? So what we will do, we say train dot is null of. This null of nothing is nothing but it shows whether the particular row is going to be null or not. Null in the sense it is not having any value or it is having NA value. Right. Now I see down. Yes. So we can see here that we are having totally 891 rows and 12 columns, and you can see that I am having some age value also to be NA. This is actually an NA field because it is returning true. And if you see the cabin column, this cabin feature is also having many true values, mean that many NAs are actually present in cabin also. So what we have to do, we need to act on these age as well as cabin values. Before actually acting on these values, we need to understand clearly that whether any other features is also having NA or not. So what I will do, I'll go for a heat map. This heat map, what it will do, it will take the train all the NA values, and I'm not having any y axis here. and column bar is not there, and the heat map feature what I'm going to use is Viridis. Right? If you see this particular heat map, I can say that these full blue values meaning that there is no NA values here or here. But when I see the age feature, there are some yellow lines drawn in between, meaning that those particular rows are actually having NA values for age feature. Similarly, the park, target, ticket, fare, these are also not having any NA values, while cabin is having many NA values way because many thick yellow lines are actually present in between these distribution. But other things are not having any NA values. So what we have to do, these NA values need to be removed before we go for any analysis or any learning algorithm application, right? So what we have to do, first we need to understand the use of these individual items. What is the feature of passenger ID, survived, P class, name, gender, SIP, park, ticket, fare, embarked, everything I need to understand what exactly they mean, whether there can be any relation that can be brought between those particular features with respect to age or cabin. I have to identify that first. The one of the easiest step is just to don't we don't see anything, we just remove the rows which is actually present. If I remove, what will happen, if I remove age, many of the rows will be deleted. But if I remove the NA values in the cabin, almost all the rows will be deleted, which is actually extremely unfair. So what we do, we actually go for a statistical technique. So before going for application of either statistics or model building or deletion, let us first see the features of each particular feature available, right? So the first one what we take is the survived data. See how the survival rate is there. 0 means that the the passenger hasn't survived, and 1 represents that the patient and the passenger is survived. It is found that many of them died and only few of them are alive. Right? This is actually from Titanic data set. Hope many of them have seen the movie. Many of them have died and only few are actually existing. Right? Next, what happens is, now I found these plots. Next, I was willing to see the comparison between survived as well as the gender. So I take the sex column also into play. This hue parameter is nothing but I need to color my distribution based on the gender. So how many gender is there? I am having 2 genders. So 2 colors are formed, right? If you see this, we can find that more males are died and less number of female only died. And more females are saved and less number of males only is saved. So there is some sort of comparisons that can be existing between survived as well as gender. I can do that. Next is actually the passenger class. Now I take the hue with respect to passenger class, and what I do, I see the survived data. See the passenger class, I'm having totally 1, 2, 3. First class, second class, and third class is available. If you see here, if a passenger is traveling in third class, then the possibility of him to die is actually high. And if the passenger is in the first class, the possibility of him to get saved is high. So this is actually the comparison we get. So we get the comparison of the survival rate based on both gender as well as the class, the passenger class. Next we come to the age. Now what I do is, yes. Now I take the passenger class and see, and next I take the age. I just train age dot drop NA. Right? I'm going to drop the NA values. So what is the thing here is, now I'm going for the first step, that is deletion of the entire row if I found an NA value, right? And I'm going to construct bins of size 40. Now you see that there is no normal distribution exactly found, but if I remove these initial ages, it can bring to some normal distribution curve. Normal distribution is nothing but a bell-shaped curve, that is right. So this is not an exact normal distribution, but I can say a nearly normal distributed curve. Right? I reduce the bin size, and this alpha is actually for the color strength. How much thick my histogram should be there? Only 0.3 I give. This is not a very good, very important parameter here. Now we just reduce the bin size to 30, and we are actually plotting it. Yes. Now I can see that what I am ultimately saying is this distribution is going to be as normal as possible. Why we are very keen about that normalization parameter is nothing but when any data is normal, then it means that there exists some pattern in the data. if I found a pattern in the data, then the missing NA values can be filled based on that pattern itself. Because in normal distribution, we can clearly say that in a particular place, if it is 15 or 16, the corresponding value should be this. Like that, we can clearly say. Why? Because normal distribution says that the curve should follow a bell shape. If bell shape need to be formed, we can easily say that this particular position should have this value, this particular position should have this value, like that. So only we are every time we'll be more keen about finding the distribution's shape. If the shape of the distribution is known, then it means that we can easily determine all the parameters with respect to that particular feature, right? Then we see the other parameters which are not that much explanatory. That is SIBSB. If you see SIBSB, we see that how many SIBSB is there. From 0 to 8 it is there, but not giving that much importance here. We don't find any pattern here. Similarly, I take the train fare. Train fare is also not normalized distributed. I'm just analyzing all the features available, right? Next time, these are the features we have seen everything. What are the features that is actually left out is name as well as the passenger ID. So name is not going to give us any information. Passenger ID is also not going to give us any information, right? So these things we actually see. Now the features which actually help us more in analysis is nothing but the gender data, next the survival data, next is the passenger class, which is having some close relativeness. I can give some related view on those kind of stuffs. Next, what I go is I go to a cufflink package. I'll explain what is cufflinks first. Cufflinks is actually another package in Python for data visualization, which combines your pandas data frame with plotly package. Plotly has many graph visualization schemes, and this cufflinks can link a pandas data frame to a plotly package. So we use the cufflink and say cufflink.go underscore offline, mean that if I have a data set here, even though it is not streaming, it will give us a floating data. If I change the data, then dynamically the plot also will change. So it says go offline. Now I come here, now analyze the train fare. This is actually how the cufflinks will work now. I use iPlot instead of normal plot. So just drawing the histogram. I'll go directly into the data cleaning phase. That will be actually most important here. Yes. See, I'm taking the P class and the age. So with respect to the passenger class and the age I'm taking, and if you see here, I could get a box plot here. I was actually plotting a box plot, and in this box plot clearly says what is the median portion and what is the 75 percentile value and what is the 25 percentile value. That actually is a box plot parameter. This middle line says that what is the median of the distribution, and this particular line says what is 75 percentile of data, and this line says what is the 25 percentile data. Now coming to here, this is actually the mean, and this is 75 percentile, and this is 25 percentile. And here this is the mean, and this is 75 percentile, and this is 25 percentile. Now what I say, now the distribution I find that okay, this is actually a good kind of distribution where I could get a mean value around some 37, and here around some 28 or 25, here is around 25, and so on. So I could find the mean value, I can see the distribution, how it is actually floating. If you see this box plot, I can easily visualize that the data is actually somewhat close, meaning that it was actually having not much deviation from the minimum value to the maximum. You see, the minimum value is actually over here, maximum value is over here. Though the maximum value is somewhat higher than the minimum value, but I could find some close distribution in other ranges. Here the range between minimum to mean as well as maximum to mean is actually very close. Here also the same, meaning that okay, the age is actually somewhat equally distributed in passenger class 2 and 1, compared 2 and 3 compared to passenger class 1. In passenger class 1 also the age is actually somewhat closer to the mean, and the maximum age is also somewhat closer to the mean, right? This is what we have, right? Now using this information, what we are actually going to do is, we have many NA values present here, and my first step is to replace that particular NA value with the mean value. This is actually the mean, I'm going to replace it. So what I do, Now I take in the age imputation. Imputation is nothing but updation of NA values. So I take the age. So age is equal to some calls of 0. That is a parameter which is going to be obtained by this function. What it is going to do is, if a particular age value is going to be null, it is what is going to do is, if p class is equal to 1, return 37. Else if p class is equal to 2, that is class 2, the second class, it is going to return 29. Else it is going to return 24. Right? What is this 37? What is this 37? Yes, what is this 37? Can anyone say what is this 37? Yes, if you see here, what is this 37 value? We have the range over here in the mean. What is that is? This box plot says that this 37th value is here in the mean. I'm replacing the NA values with the 37. Can you understand it or not? Students, can you understand it or not? Yes. So again, what is this next value? That is 29. What is this 29? What is this 29?
How can we say that exactly whole number value it will be, sir? Okay, can it be a fraction of them?
Age cannot be a fraction, so we take the round. Age cannot be a fraction.
Median, sorry, mean, sir.
Yes, mean can be a fraction, but age cannot be a fraction, right?
Yes, sir.
So we just round it off. Good question. Age is, it may be a fraction, but since age cannot be a fraction, I'm just substituting the values. This is actually hard coding, right? I'm not directly taking it. I'm just hard coding the value by seeing the box plot. Similarly, I take 24 for here. This is the mean goes around this, so I take this and then I plot here. So this is the age updation with respect to the P class. Now I just apply with respect to this, and the train age is actually computed. And if you see here, if I do the heat map again, now there is no NA values present. Why? Because all the NA values are replaced by the conditional mean. So with respect to what age is replaced now? Quickly say. With respect to what condition age is replaced? With respect to what age is actually replaced?
Conditional mean.
Yes. So with respect to which particular feature it is conditioned?
Sex.
No, it's we took gender as well as survival rate, but finally what we took here?
Age.
Age with respect to, see here, P class. We draw the box plot with respect to P class only. Now if you see here, we took the box plot with respect to P class. So I just take X as P class and Y as age. Based on the P class, it is conditioned and the mean is taken. Because if I use P class, I get 3 different conditional means. So like Devendra asked during the last class, right? So if I replace all the NA values with mean, then all NA values will have same value. Now here, all NA values will not have same value. NAs will be divided into 3 blocks. If it is class 1, it will have the same value of this 39. And if it is of class 2, it will be having 29. If it is class 3, it will be having 24 or 25. So this is actually the thing. So now, Devendra, are you clear now, right? Now this time, all the NA values will not have the same mean. They'll be having 3 classes of mean. Clear, right, Devendra? Yes. Now the next step, what we have to think is, we have to think about this cabin, right? This cabin is going to be having more NA values now. Now I need to remove this cabin NAs, right? So what we can do, we can actually think of first is actually dropping the cabin values. So train dot drop of cabin x is equal to 1, in place is equal to 2. So there is a parameter in place is equal to true. The default value of in place is false, meaning that action will be taken, but the operation will not be done in the object if in place is equal to false. If in place is equal to true, then the action, that the dropping operation will take place, and the result will be substituted in the train data frame itself. Otherwise, if I say in place is equal to false, I should write it as a is equal to like that, and here I need to make it as false. Default is also false. If I make it in place is equal to false, train will have the cabin value, but A will have the same complete train features from passenger ID to embark except cabin value. A will not have cabin value, but train will have cabin value. Instead, if I make in place is equal to true, train will not have cabin value because I'm executing it and substituting the result in the data frame itself. Now I get the train that head. Now you see cabin value is not present. Right, cabin value is not present. I'm just substituting here just for ensuring that there is actually no NAs here. Just for ensuring it, I'm again saying train dot drop NA in place is equal to true. Actually, it is not going to create anything. Just for dropping it, right? Now, what we are going to do, we are going to convert categorical features into that is now numerical values, right? Actually, and we have something called as dummy variables in Python. So, what is a say for example, if I want to have my city, right? Many of you will be saying, what you said city, I'll be saying Madurai, somebody will be saying Chennai, Trichy, like that, they'll be saying. So what I can do is if I put a dummy variable substitution for those, then what will happen? All the Madurai will be replaced with 0. All Chennai will be replaced with 1, all Trichy will be replaced with 2, all Guntur will be replaced into 3, and so on. So everything will have some numerical values. That is actually dummy creation. So I just create dummies for embarked data. So if you see in the top and the train.info, this embarked is going to be an object type. It is not an integer type, it is an object. So I want to, if you see the data set again here, when I print the embarked data, this is saying some SC like that, it is actually saying embarked. So what we can do, we can replace this embarked values with some zeros and ones, because we know that many learning algorithms work on only numerical floating point values. So we need to convert these into some numerical values. So I create dummies for the embarked feature. So I create dummies. Now I create here. So if I create dummies, the categorical features can be converted into numerical values. So I create dummies for embark and drop underscore first is equal to true. Meaning that if I say drop underscore first is equal to true, it is actually going to omit my column feature name. Right? Now I just remove the head. Now I get the dummy values be created. That is 1, 0, 1, 1, 1 and so on. This is actually being created. So if you go up and see, now actually yes, all the S is actually replaced with ones and the C is actually replaced with 0. That is what we get 1, 0, 1 like this. Right? Now what we do, now we go into the dummy value creation and comparison it with some sex. Right? Here in sex I'm having both male as well as female. If I create dummies for the sex I'm having, so I can make male is equal to 0 and female is equal to 1 like that. I can get for the gender also. So gender also will be created dummies. So that is actually I'm saving it in some sex node variable, and this embark is also created dummies and it is stored in a variable called as embark. Just I'm creating dummies and storing it in a data frame, that is sex as well as embark. Next what I do, I actually drop from train these features. Sex I'm dropping, embarked I'm dropping, name I'm dropping, ticket I'm dropping. Now we need to understand why this dropping is actually taking place. This sex I'm dropping because I'm having a new sex value that I need to put. This is actually will have a value like male, female like that. This embarked will be having a value like SC and so on. This name will be having a full name will be available. And I think that this name is not going to give me any particular feature. So I don't want this. I remove this name also. Next, ticket. This ticket is also not going to give me any information on the analysis. So I remove all these 4. Next, what I do, once I remove, I just put head. Now in this train data set, you will not find sex, embark, name as well as ticket features or columns available. Now only these features are available. Next, what I do, I say train is equal to pd.concat. So concat is nothing but it is going to merge the data frames. This train data frame is already having passenger ID, survived, P class, age, zip, park, and fair. And I'm going to concat it with other two variables, that is sex as well as ember. Where this actually came from, I have already created dummies for him. That is, I already converted those male female categorical values into zeros and ones, and S C embarked values into zeros and ones. So that I'm having in this particular variables. These variables I take and then concat here. Now if you execute the train head function now, you'll be having seen that passenger ID survived, B class, age, zip, park, fare, see, male, and these QS values is also present. See, so this is actually sex should come here, but I think male came. This is actually an error. So it is actually sex, and this is the impact values. Now what I'm going to do, I'm going to remove the survived also. Survive also I'm going to remove. See why? Because I'm going to have some survive as my output variable kind of. I'm going to create a model to find the cabin value. So now because more values are actually missing, if I replace all the values with all the that much NA values with a common value, then it will not be a very high bias. So what I do, I'm going to create a model, and the output of the model is going to be survival. So I drop survive from the train data. So this is actually the train data model, the train of survive.head. So I get the survival data alone separately. Now, just from SQL under model selection import train split, I split the entire data. That is the train dot drop of survived. That will be the entire feature. That is except survived, all other data will be the input, and survived alone will be the output, and test size is going to be 30%. Random state I give a random value so that randomly my training and testing can be fixed. I repeat again, the input is going to be all the features in the train data set except the survived field. Output is going to be the survival field, and test is going to be 30% and 101 is a random state. Now going here, I'm going to train my data with some logistic regression. Right? I come here, log model dot fit xtrain and ytrain. I'm just saying that the model dot predict of x test. See, next I'm saying log model is equal to logistic regression. That's it. Log model dot fit of x train comma y train. I'm just fitting the model. Now my model equation is ready. Now I can do some predictions over it. Log model dot predict of x test. Next, from SQL learn import, I'm just going for metrics now. That's it. We are just using the regression model is just import the model, fit the model with respect to inputs as well as outputs, then do the predictions. My prediction is going to be with respect to the survival rate. I'm going to do the survivals, and it's SQL matrix or confusion matrix. I'm predicting the accuracy of the model. And this is actually the confusion matrix. 149 times true is recognized as true itself. 65 times false is recognized as false itself. So it is better. The overall accuracy is going to be 80% obtained from the accuracy metric by the accuracy core based on the test prediction. Right? And my test prediction values for the survival rate is over here. The thing is, we take a data set, we clean the data set and apply logistic regression model over it. So what are the steps we follow? We generally know that deletion, model creation and statistics are the primary steps. When we go for deletion, if you have a very large data set, then I go for deletion of NA values. If I have very small values and less amount of features only, then I can go for model creation. If I use statistics, then it is actually somewhat efficient. But the drawback, as said by Devendra, is nothing but if I have more NA values, if I replace all of them with a common value, then bias will increase. So what I can do some conditional mean activities. I can take the comparison of other features to find the NA values of the subsequent feature. So what we have to do, we have to individually analyze by visualizing visualizing the feature of each variable, starting from passenger ID, age, survival rate, passenger class, everything we are actually visualizing, and based on those visualization, we found that okay, passenger class is going to give me three different variables, that is 1, 2 and 3. And based on that, if I take a conditional mean, I'm going to get some three values which can be substituted for the age values. So those age I'm actually substituting. Now age NA values are removed. Then I go for the cabin value. Since it is having more number of variables, we actually act on it by dropping those NA values and then going for the survival model creation, right? So this is the what we do it in the model cleaning as well as creating a log model. Creating log model is additional actually. We are just seeing how the data cleaning can be done on the missing data and how it can be used for performing some analyzing models. In addition to these missing data classification, we also know that we have a function for cleaning, which cleans NA values as well as infinite values, right? So like drop NA, drop INF. Drop NA and drop INF functions can also be used to drop those higher, very high values or NA values. I can drop those also, right? Now I'm making it clear on how to work on missing values and infinity values and do regression analysis. So how to do that, and if what I will do this in quizzes or exams, what I will do is I'll be giving you some data set with NAs and I'll be asking you to substitute those NA values. In practical, what I do, I ask you to do the thing for a very big data set. In small quizzes, I'll be asking you to substitute those NA values with some nice values. How can I do those? What are the three? State any three good values for these, like that, so that you can actually do a conditional mean or conditional mode or normal mean, anything. You have to say me what are the ways in which I can substitute those mean values, right? That is easy, right? If I give you some 20 records in a particular data and ask you to substitute those NA values then and there with some good values, then how I say good values before analyzing is, if the values are not most of the values are not common, then I say it is good. It should be varied value. How it can be varied? If I do a conditional operation, it can be varied, or if I do a regression model for that, it will be even more effective if the data set size is very small, right? So this you can easily do, right? Those missing data analysis. Yes. Yes or no?
Yes, sir. You can
Yes.
try.
Yes. Yes. In the try in the sense, it is very easy. For example, in assignment also I have a problem like that. That is 20 the rows will be given. In the 20 rows, totally 5 features are available. In any one or two features, NA values will be available. What will be your step? You should first, you can, if the 20 rows are available, if some of you think that if you want to apply linear regression model to calculate those NA values, then you are great. If you don't want to do that, then you can actually use those conditional means or last value first or conditional mode and those kind of statistics to find those NA values. So how good your NA value should be is, your NA value for that particular feature, what you are substituting should be random to a particular extent. Not all of the NA values should be substituted with the same value. It should be somewhat deviated also. If I take the mean and substitute, it means that all the NAs will have same values. There is no use in doing that. So instead, what you can do, you can substitute it with some varied values based on some conditional activities, right? That you can do, right? Yes.